In this video, I'll be showing how to draw various LP constraints using the graphical approach. All variables will be assumed to be non-negative, so we will stay in the first quadrant here. The typical LP constraint is of the form 5x plus 4y less than or equal to 20. To draw the constraint line, we only need 2 points, and we often use points where x and y are 0, since those are easy to calculate. So when x equals 0 here, y is 5, and when y equals 0, x is 4. Joining those 2 points, we have the constraint line. Since this is a less than constraint, it will be satisfied below the line towards the origin here. And if it were a greater than constraint, it will be satisfied above the line away from the origin. Other basic constraints include those with vertical or horizontal lines. For example, to draw x less than or equal to 3, we start by drawing a line at x equals 3 and shading the region to the left of it. And for x greater or equal to 4, we shade the region to the right of 4. Similarly, for y less than or equal to 2, we shade the region below 2, and for y greater or equal to 3, we shade the region above 3. Sometimes our constraints involve fractions. Consider these constraints here having fractions with denominators 4 and 5. A good way to start is to clear the fractions. This can be done by multiplying both sides of the inequality by a common multiple, like 20. And that gives 5x plus 4y greater or equal to 20, which, as we saw earlier, is satisfied above the line here. And if we have decimals, as shown in this inequality, we can also first clear the decimals by multiplying both sides by multiples of 10, based on the number of decimal places we have. Since the maximum we have here is 3 decimal places, we can first multiply both sides by 1000, and if we now divide both sides by 25, we have this initial inequality, which is satisfied below the line here. Now consider this constraint with negative coefficient. When x is 0, y is 1. When y is 0, x is negative 1.5. This second point can be plotted somewhere to the left here, but I'm just going to find another point that does not involve a negative value. This is because sometimes the negative value is too far away, and using it makes the feasible region appear too small. So I'm going to find another point that will fall into this quadrant. I will pick a value for x or for y, whichever is more convenient, and calculate the other. I can rewrite the equation of the corresponding line as 3y equals 3 plus 2x. So when x equals 3, 3y equals 9, and y equals 3. And here is the equality line for the constraint. To determine the region satisfying the constraint, I will pick a point on either side of the line to be sure. The origin 0, 0 is always an easy one to use. When both x and y are 0, the left side of the inequality is 0, which is less than 3. So the inequality is satisfied in that direction. Note that if I pick a point on the other side, for example 0, 3, I obtain 9 on the left, which is not less or equal to 3. Now suppose we have the inequality 2x minus 3y greater or equal to 3. When y is 0, x is 1.5, and when x is 0, y is negative 1. 0, negative 1 can be plotted down here somewhere, but again, I'm going to find a positive value. I can rewrite the equation of the corresponding line as 2x equals 3 plus 3y. Thus, for example, when y equals 2, 2x equals 9, so that x equals 4.5. Here is the equality line. Testing the constraint at the origin, we see that 0 is not greater or equal to 3, so the inequality is not satisfied in that direction. But 4, 0 here gives us 8 on the left, which is greater or equal to 3. So the constraint is satisfied on the right here. Other important types of constraints to consider are those with zero right-hand sides. For example, 3x minus 4y less than or equal to 0. This constraint line can be written as 3x equals 4y. So when y equals 0, x equals 0. That is, the line passes through the origin. For a second point, we can conveniently choose y equals 3, so that 3x equals 12 and x equals 4. Here is the line. So which region satisfies this constraint, A or B? Again, we can pick a point on either side. Unfortunately, 0, 0 cannot be used because the equality line passes through it. Checking the point 0, 2, we have negative 8 on the left side, which is less than 0. But the point 2, 0 gives 6 on the left, which is not less than or equal to 0. The constraint is therefore satisfied in this upper direction. Finally, we also have equality constraints that are only satisfied on the line, not above it and not below it. And if an LP model has one of these equality constraints, the feasible region will always be on the equality line. And that's how to draw most common types of linear constraints graphically. Thanks for watching.